Alright, so in today's tutorial video, I want to look at statistical methods for analyzing two sample data in R. But before we proceed, I urge you to kindly take a look at my previous tutorial video on the flowchart for classifying data, because in that video tutorial, I illustrated and explained the data structure for two sample data, which will help you to catch up with everything that I'm going to do in today's tutorial video. So now let's get started. So like the one sample data, we have parametric test and non-parametric test for analyzing such data. The same applies with two sample data. The parametric test for two sample data is known as the two sample T-test or the independent T-test, which basically compares the means of two separate groups to determine whether statistical evidence shows that the associated population means are significantly different. Okay, for example, researchers may wish to compare the mean income level of two regions or the mean effectiveness of two drugs. There are certain assumptions which must be satisfied before we make use of this test. One of the assumptions is that the data must be continuous. The next one is that the two samples are independent. The next one is that data must be normally distributed. And the last but not the least is that the variances of the two populations are equal. Okay, this is an asterisk because even if it is not satisfied, we can still make use of the two sample T-test. We just have to specify in our computation that the variances are not the same. Okay, now let's take a look at the non-parametric test for two sample data. This is known as the Mann-Whitney U test or the Wilcoxon Rank Sum test. This basically compares the medians of two separate groups to determine whether statistical evidence shows that these are associated population medians are significantly different. Okay, for example, researchers may wish to compare the median income level of two regions or the median effectiveness of two drugs. There are certain conditions which must be satisfied before we make use of this test. One of the conditions is that the data must be continuous. The next one is that the two samples are independent. And the last but not least is that the data must not be normally distributed, not necessarily be normally distributed. Okay, let's take an example. Using the iris dataset as a researcher, you wish to compare the average sepal length of the Setosa and Virginica plants from the iris dataset. Perform statistical analysis for this data. So before we jump into R to begin, let's take a look at the iris dataset in the CSV format. So this is the iris dataset, and this is a clean data. Okay, before you analyze any data set, you have to ensure that you have gone through the data cleaning stage. If you want to learn how to do this, you can watch my previous tutorial video on spreadsheet data analysis in R, where I included the data cleaning in the course of the tutorial. Okay, so the problem here is that I want to find out if the sepal length, right, for Setosa and that of Virginica are the same or not. So first of all, we can filter the sepal length for Setosa. So this is sepal length for Setosa starting from observation 2. So we can scroll down. Let me try and highlight it. So this is for Setosa. Okay, it ends somewhere here. So I think it ends here. Okay, so that's the end for Setosa. Then we also have to scroll down and get that sepal length for Virginica, which starts from here 101. Okay, also have to get its values. Right, once we get the values for these two species, then we are supposed to find the average value for this for Virginica and also find the average value for the sepal length for Setosa and try to compare if the difference in these two means or medians, let's say the difference in these two average values are basically different from 0 or they are equal to 0. That's basically what we want to do. Okay, so let's try and jump into R to begin. Alright, so in R first we would like to clear all our working and graphic windows. So if you have yours clean as mine, you can just skip this, okay, and just go to proceed. But if you don't have, you have to clear and clean all your graphics and environment windows. So let's proceed to import dataset. This is a CSV file, so I'm using the read.csv, and file those choose to basically choose from the folder where I have my data file. So I'm going to run this, and I'm assigning my dataset to IDAT. Okay, so let's run this. So there should be a pop-up window for me to navigate and pick my data file. Okay, So I think it's still running. Okay, so I have my data file here and R to sample data. So this is my data file. I'm going to leave this in the description of the video so that you can download it. Okay, so let me open. Once you import your data set, you should have an information in the environment window which shows that indeed you have imported your data set. So let's see. So here we go. So we have IDAT 148 observations of 5 variables. So we can view this data set by running this code offline, or basically clicking on this to view the data set. Okay, so let me clean this. So once you click on this, you should have the data set should display in a spreadsheet form. Yeah. So here we go. So that's the data set, which is similar to the one that we saw in the CSV format. Okay. So now let's get the structure of our data set now. So to get a structure, let's run this. So you can see that basically the attributes for zipper length, zipper width, petal length, and petal width are all numeric. But if you look at that of species, is in string. So in our data manipulation, you are supposed to encode this by basically converting the string to numeric, or basically assign values to the labels of the species, because this is a categorical variable. Okay, so you are supposed to convert it from string into a factor. So let's basically do that. So in our data manipulation, we need a library known as the dplayer library, which is very vital for data manipulation. So let's run this. If you don't have this installed, you can go to packages, right, and make sure that you go to install, and make sure that you're connected to the internet, and just type the name of this to install. Okay, I have already done this, so I'm going to skip that. Okay, so once you load the library, we can then proceed and try to start with the recoding. So I want to recode a species from string to numeric, and I'm assigning everything to new data. So for my imported data, I want to use the mutate function to basically add another variable to my existing data set. So here, if I'm to ignore the species 1 to species, it means that I've assigned my transformation of the data, right, to the previous one. So it's going to override the previous species. I don't want that. I want to give it a new name like species 1, so that this transformation will not have effect on the previous one. I just want to have it separate. So let's try and execute this. So basically we are converting the previous species into a factor, okay, or into a categorical type. So let's run this. So once you run this, you should have information here which shows that that's imported. I think it's still running. So once we are done, we can get the structure of our data set. So here we go. So once you click on this, let's see. So we have added another species or another variable to our existing one. Okay, let's try and get a structure now. So let's run this. So if you look at the previous one, is still character, or it is in a string form. But if you look at the new one, you can see that this is now a factor with 3 levels. So the levels 1 has been assigned to the first level, which is Setosa, 2 will be assigned to the second level, which is Versicolor, and 3 will be assigned to the last level, which is Virginic. Okay, so now we can basically drop this if we don't want to, okay, because we don't need these variables. So this is optional. I just want to remove this and basically rename the variables as well. So let's do that. So let me highlight this. So for my new data, I'm still using the new data. I just want to select right from the new data. I just want to select the species, but this time with a minus sign, I'm trying to delete it. And I want to rename the sepal length as SL, sepal width as SW, petal length as PL, petal width as PW, and species 1 as SP. So let's run this. Alright, and now let's take a look at the table. This is going to give us the first 10 observations. So once you scroll up, you see that the name of the variables has been changed. We have also deleted the previous species and maintained a new one, which is now a factor. Okay. Alright, so the next thing is to basically filter the sepal length, right, for that of Setosa and that of Virginica, okay, and try to proceed from there. So let's get this. I'm going to filter the Setosa of the sepal length, and I'm assigning my data now to G1 underscore SL. So for my new data, I want to filter Setosa from species, and I'm interested in the variable is sepal length. Let's try and run this. So once we are done, we have the information here. Let's click on that. So that is a length for Setosa. Let me close this. Let's go back and get that for Virginica. So this time I'm assigning my data to G2 underscore SL. So for my new data, I want to filter the Virginica from the species, and I want the variable sepal length. So let's get that. Let's run this. So we have an information here. Let's click on that. Okay, so we are good to go now. So the next thing is to basically do some exploratory data analysis right before we can know whether we are going to make use of the two sample T-test or the Mann-Whitney U test, okay? But this will be similar to the one that we did under the statistical methods for analyzing one sample data in R, okay? This we basically use the same information, okay? We extracted or filtered that of the Setosa of the sepal length for Setosa, and we also filtered that of the sepal length for Virginica, okay? And in our expert data analysis, we saw that the data or the distribution of the sepal length for Setosa and that of Virginica were nearly symmetric, and there were other information that we also obtained. So if you want to learn how to do the expert analysis, you can basically take a look at my previous tutorial video on the statistical methods for analyzing one sample data in R. Okay, so in this tutorial session, I'm going to basically skip the GDA because it will be similar to the one that we did under the one sample data. So you can take a look at it if you want to basically learn how to do that. Okay, so the next thing that I want to do is basically do the test the assumption of normality. Okay, because already we know from our data set that the sepal length is continuous, so the first assumption is satisfied. And with regards to independent, we know that the Setosa group is different from that of the Virginica group, okay? So this makes it to be independent, okay? Because the sepal length for the Setosa is way different from that of um, Virginica. Virginica is different, so this makes the groups to be independent. So the next assumption to basically test for is the normality assumption, okay, which is very vital. So let's quickly do that. So here I'm going to make use of the Shapiro-Wilk test. That's the first test of normality. We have other tests like the Anderson-Darling test and the Shapiro-Wilk test, which we'll be looking at very shortly. So with a QQ plot, basically it draws the correlation between a given sample and the normal distribution such that if the data is approximately normal, then the plot will closely resemble a straight line sloping upwards to the right, okay? But before we get a QQ plot in R, we need a library known as the QQ plot R. So let's try and run this. If you don't have this installed, you have to click on install and basically get that, okay? So now let's get a QQ plot of the sepal length for Setosa. Okay, so in here, I'm assigning my plot to QP1. So QQ plot, GNG plot, the data, first argument is the data for Setosa, and this argument, the static mappers, we are interested in the variables, so the variable is sepal length. So I want to add a confidence band together with a QQ line, right? That's the straight line that we are going to see in a point. And I also want to give you some labels. So on the x-axis is theoretical quantiles, y-axis we have sample quantiles, and the title is going to be QQ plot, right, of the sepal length for Setosa. So let's try and run this. Control enter. So I think, yeah, so it's still running. Once it's done, we should see some information there in the plot window. It's still taking some time, I don't know why. So once we are done with this, we can get that of the QQ plot of the sepal length for Virginica as well. Okay. So I can assign my data to in here. I want to assign my data, my graphic plot to QP2. So the from ggplot, the first argument is the data. That's the data for Virginica, and the static mappings I'm interested in the variable of sepal length. So everything follows like the first one. Then you can also run this. I don't know why it's taking so much time. Oh, I don't know why it's taking so long to show me the result. Okay, so I'm going to skip it for now. Once it pops up, I'll go back and interpret that. So we have other tests that you can also rely on, like the Shapiro-Wilk test and the Anderson-Darling test. So with the Anderson-Darling test, we need a library known as the not test library. So let's try and get that. So let me execute this. Oh, I think we are supposed to see the first result. I don't know why it's taking so long. I don't know why. I don't know. Let me try and rerun the first one again. Alright, so here we go. So this one is given as a QQ plot of the sepal length for C2. And we can see that the points are within the confidence bound, right? And they also on the straight line sloping upward to the right. So this indication that the distribution of the sepal length for C2 is normally distributed. Okay. Now let's take a look at the second one. So this one is for Virginica. So you can see that some of the points seems to deviate from the confidence bound, but you can see that most of the points are on the straight line sloping upwards to the right. So we can also say that the distribution of the sepal length for Virginica is normally distributed. Now if you look at this plot, you may have some doubt. So that's the reason why you have to rely on other tests of normality like the Anderson-Darling test and the Shapiro-Wilk test. So let's try and get a library for Anderson-Darling test. Once we load this, let's try and execute the Shapiro-Wilk test and the Anderson-Darling test for the C2 data. So this one will give me that of the Shapiro, and the second one will give me that of the Anderson-Darling test, right, of the sepal length for C2. So let's execute this run. So let me scroll up. We are interested in the p-value. So if you look at the p-value from the Shapiro-Wilk test is 0.325, and if you look at that of the Anderson-Darling test is 0.2879. If you are to compare this to the alpha level at 1% or 5%, it means that we are going to fail to reject the null hypothesis. We only reject the null hypothesis if this p-value is less than or equal to the alpha level at 1% or 5%, okay? So the null hypothesis for these two tests states that the data is normally distributed. So if you are failing to reject the null hypothesis, then it means that it follows that the distribution of the sepal length for C2 is normally distributed, okay? Now let's take that off the Virginica. So this one is going to give me the Shapiro-Wilk test and the Anderson-Darling test for the Virginica data. So let's try and run this. Alright, so if you scroll up, you can see that the p-value, right? Let me scroll up. Oh, why is it? Okay. So the p-value, this is the p-value from the Shapiro-Wilk test, and this is the p-value from the Anderson-Darling test. You can see that these p-value are greater than the alpha level at 1% or 5%, so it means that we are going to fail to reject the null hypothesis and conclude that the distribution of the sepal length for Virginica is normally distributed. Okay, so now that we are clear that the normality assumption has been satisfied, it means that we are going to make use of the parametric test, which is the two sample T-test. So let's quickly proceed to that. So the null hypothesis here is that the mean value of the sepal length for setosa and that of virginica are equal, and the alternative is that the mean value of the sepal length for setosa and virginica differ. Okay, but before we make use of the two sample t-test, there was one assumption that we have to check, that is the test for homogeneity of variance. If you can recall, the fourth assumption under the two sample t-test, we saw that we had one in asterisk which states that the population of the two variants must be the same. Okay, so in order to test for that assumption, we make use of the f-test or the Lebanese test. Okay, so that is how we can test for homogeneous variance in R. Okay, so but before we do that, let's create a new data frame. I want to create a new data frame. Okay, and in this data frame, I'm trying to combine these two data. That's the data for setosa and that of virginica as one. So the group, I'm trying to repeat this. I'm trying to repeat S 49 times. S denote that of setosa, and I'm trying to repeat V 49 times. V stand for virginica. Okay, and the values is going to entail that of the sepal length for setosa, and the second argument is going to entail the sepal length for virginica. Okay, and I want this string that I've created in the first group to be factors. So let's run this. Right, so let's click on the data frame to see now. So I'm just trying to combine the two data as one. So the first one, SS, stand for the setosa, right? And the second variable is the sepal length. And if you scroll down, the variance stand for virginica, and these values are the sepal length. Okay. So now that we are done with this, we can proceed and get the test for the homogeneous variance using the f-test. Okay. So in R, to get an f-test, we make use of the var.test function. The first argument is that of the sepal length values, and the second argument is the categorical variable, which is a group. Then data is going to be data frame, and we also have alternative to be two-sided. Okay, so let's run this. Control enter. So if you scroll up, we have this information f statistic. Okay, now with the f test, it is just a general term for any statistical test in which the test statistic has an f distribution under the null hypothesis. Okay, so basically it is used in comparing variances of two normal distribution. Okay, and we know that if you take the ratio for two chi-square random variables, we get the f statistic. Okay, so this f statistic, there are two ways in which we can get this. Because the mean value of the f distribution is approximately 1, it follows that if the null hypothesis is true, then the ratio of the two sample variances will be equal to 1. Okay, so if that's the case, then we have to compare this to 1 to see if it is close to 1 or different from 1. Another way is that because the f score from the f distribution is greater than 1 or equal to 1, the ratio of the f-test can be arranged so that the numerator of the ratio will always be greater than the denominator. Once we do this, we get the f statistic, which will be compared to 1 to see if it is close to 1 or it is far from 1. Okay, so if you look at the p-value from this f-test, we can see that it is almost less than the alpha level or the threshold value at 1% or 5%. So it means that we are going to reject the null hypothesis and conclude that the homogeneity of variance for these two groups is going to be false. Okay, so the variance within these two distributions, that is that of the sepal length for setosa and that of virginica, they are not the same. Okay, another way to get the test for the homogeneity of variance is to make use of the Lebanese test. In R, to get a Lebanese test, we need a library known as the car library. So let's load this. Once we are done loading, we can then get the Lebanese test. So the first argument is sepal length values, and the second argument is that of the categorical type as the group, and the data is data frame. So let's run this. So if you look at the p-value from the Lebanese test, if you have to compare this to the alpha level at 1% or 5%, it means that we are going to reject the null hypothesis and conclude that the homogeneity of variance for these two groups they are not, or they are not the same. Okay, so once we have this information, we can proceed and make use of the two sample t-test. Okay, now one thing that you have to note with regards to the t-test is that we know that from books there's this condition that the before we can make use of the t-test, the sample size should be smaller. Okay, it should be less than 30. But one thing that you have to note with regards to the t-test in practice is that it is also a symmetric distribution, or a family of curves that is based on the concept of degrees of freedom, which is related to the sample size. So as the sample size increases, the t-distribution approaches the standard normal distribution. So even if you have a sample size that is more than 30, you can still make use of the t-distribution, or sorry, the t-test. Okay, you can still proceed and make use of the t-test even if you have a sample size that is more than 30. So in here, the first argument is going to be that of the sepal length for setosa, the second is the sepal length for virginica, and the alternative hypothesis is two-sided. And we also have another argument that the equal variance here, we are setting it to false because from the test of homogeneity of variance, we saw that the variances were not the same. So that's why we are trying to set this to false. Okay, if from the test of homogeneity of variance, if they were equal, then I'm going to change this f to t. Okay, but because they were not the same, so this should be false. Okay, so now we can run this. So if you look at the mean value for the setosa, that's the sepal length for setosa, the mean value of the sepal length for virginica, we can see that this is around 5 centimeters, this is 6.6 centimeters. So we want to find out if the difference in this means is equal to 0 or it is significantly different from 0. That's basically what we want to do. And if you look at the p-value from these two sample t-tests, if you have to compare this to the alpha level at 1% or 5%, then it means that we are going to reject the null hypothesis and conclude that there's enough evidence to indicate that the mean value, right, of the sepal length for setosa and that of virginica are not the same. Okay, or basically their difference is significantly different from 0. Okay, now suppose the assumption of normality failed, right, then we are supposed to resort to the nonparametric test. That's the nonparametric test for the two sample data, which is going to be the Mann-Whitney U test or the Wilcoxon Rank Sum test. Okay, so let's assume the assumption of normality failed, then we are going to make use of the Wilcoxon Rank Sum test, okay, or the Mann-Whitney U test. So in here we are going to use the function Wilcox.test. The first argument is going to be that of the sepal length for setosa, and the second argument is sepal length for virginica. So the alternative is going to be two-sided, and in here we include as another argument exact to be equal to false. Yes, f is for false. Okay, now one thing that you have to note with regards to the Wilcoxon Rank Sum test is that it arranges the observation of the combined samples in ascending order and then substitute a rank for each observation. So in the case of ties or identical observations, it replaces the observation by the mean of the ranks that the observation would have if they were different. So in order to avoid the warning message in R saying that cannot compute exact p-value with tie, we often set the exact to false. Okay, so that's why we have here to be false. Okay, so let's try and run this. So so if you look at the p-value, if you have to compare this p-value to the alpha level or the threshold value at 1% or 5%, it means that we are going to reject the null hypothesis and conclude that there's enough evidence to indicate that the median value, right, of the sepal length for setosa and that of virginica are different, or basically the difference between these two groups is significantly different from 0. Okay, so I think this is similar to the conclusion we had under the two sample t-test. Okay, so this is basically how to perform a detailed statistical analysis for two sample data in R. Please, if you find value into this tutorial video, don't forget to subscribe if you have not, and also turn on the notification bell to get more updates anytime I post on this channel. Thank you for watching.